In this video, we're going to review the function transformations. For instance, let's say I have the function f of x, which is this green parabola right here, and it is a x squared parabola. I want to define a new function g of x as a transformation of f of x. For instance, what if my function was f of x plus 3? Okay. Well, as you can see here, this is a transformation because all my green parabola did was move up 3 units, and every point on the parabola moved up 3 units. Alternatively, I can move the parabola down by defining another function, let's say k of x, and I could say it is the function of x minus 2, right? And so that's the black function there. My original green just moved down 2. So these are called vertical translations because my parabola moves up and down. So when I added k to my function, it moved it up. In other words, my parabola moved up k units. This is f of x plus k. Right. So, and that kind of makes sense. It's kind of intuitive that up would be positive, and if I want to move it down, so if I'm going to move it negative k, right, that moves it down. So my parabola, right, so this would be f of x minus k, right? And you're probably going to want to do some color coding on the graphs today, otherwise you're going to get confused with your own notes. All right, our next ones are horizontal translations. Let's kind of preview it. We're going to do the absolute value function just to kind of make it a little different here. And we're going to horizontally translate it with a minus h. And notice it goes in the parentheses and it's happening to x. So let's say my original function is the absolute value, which is it's a line basically that gets bent here at the origin and keeps a constant y value that's positive. So it's shaped like a V here. What happens if I add 5 to x? Notice I'm making a change to x, and making a change to x is going to shift things horizontally. Now here's the funny thing about this. It kind of does the opposite of what you think it's going to do. If you add 5 to x, it actually moves it to the left. Or if you subtract 2 from x, it actually moves it to the right. It does kind of the opposite of what you expect it to do. So subtracting a number from x moves it to the right. So even though you associate negative with left on the number line, my absolute value function, f of x minus h, it moves to the right. But if I add h, it moves it to the left, right? So my absolute value function moves over here. So this is f of x plus h. One of the ways you can memorize this, which is kind of funny, is your ex lies. Making a joke about your ex-boyfriend or your ex-girlfriend. All right, the next thing we're going to talk about are reflections of functions. Let's say we have this square root function, which only exists in quadrant 1. This is the best way to see this. So if I make my function negative, right, meaning I'm making the y values negative, that's just going to turn every y value on this curve into a negative y value down here. So what this does is it kind of takes the graph and rotates it around the x-axis. But if I make my x value negative, meaning I'm making a change to x, what's going to happen is it's going to rotate around the x-axis. So making the function negative means I'm making all of my y values negative. So my square root function looks like that. That is negative f of x, right? But if I make my x negative, it rotates around the y-axis. So that becomes my function like that. And that is f of negative x. And this is showing you how the rotation happens. This is rotating like rotisserie chicken, and this one's rotating like a spinning top toy. So our next one are called dilations, where we are morphing the graph to change its shape in a way. Like we're stretching it in the x or the y direction. Now ignore how I created this, but let's say I have this like triangle function, right? It's an absolute value function where I limited its domain and transformed it, right? So we're going to call this black curve, or this black, triangle, the function. This is my f of x. So the black thing is my f of x. So what happens if I multiply my function f of x, I multiply this whole triangle by the number 3? What will happen? Well, obviously all my numbers are just going to get 3 times higher. Like right here, my highest number was 2, and now my highest number is 6. I basically vertically multiplied the numbers by 3. So it stretched it upwards. That's called a vertical dilation. So multiplying your function by a creates a multiplication of the y values by that number. So this right here is some number a f of x. But what happens if I multiply the a inside the parentheses? I multiply the x by the a. Well, since we're making a change to the x value, it is going to be something that happens horizontally. Let's find out. So here's my original function. I'm no longer multiplying outside, I'm multiplying inside, multiplying the x. And you would expect it to stretch outward, but it doesn't. It actually does the opposite. It's kind of like the horizontal translations. The horizontal dilations are the opposite too. Multiplying x by 2 made my thing skinnier. It didn't change the height of it. Notice the heights didn't change, only the width of it. So my original width was 4, and now it's half as large. So multiplying by 2 compressed it in half. If I were to multiply by 4, my width is now a fourth. If I were to multiply it by 8, my width is now an eighth. So in this example, multiplying by the a here, it does the opposite. It's like a fraction. It's 1 over a. So it stays the same height. It just got thinner, as can be seen here. And that is f of ax. Let's do a quick example. It's quick if we interpret these things fast. So we have a graph here that's defined as f of x. So this graph is f of x. We don't care what formula created it. We just know that this is a function. And we are asked to plot a new function called g. And it's got 3 transformations, right? So we have x minus 1. Okay, that's obviously going to be a horizontal translation. And then on top of that, we have a minus 3 over here. That's going to be a vertical translation. And then even on top of all of that, I'm taking my original function and I'm multiplying it by 2. Let's kind of summarize what we're going to do to f to get our result. So when I subtract 1 from x, that's going to mean right 1, and then we have to go down 3, and then we got to vertically dilate by 2. So vertically stretch it. So what I'm going to do first actually in this list of things is I want to stretch this graph the way it looks right now. That means I'm going to take it and I'm going to stretch it like a rubber band. I have to double its size. So this dot is 1, it's going to double, right? This dot is negative 1, it's going to double, right? I'm just drawing the new dots. And then this is going to double to 2, that's going to double to 6, which is off the graph up here. This is going to double to 2, and then doubling 0 is still 0. So this function, it just gets stretched. It gets larger. So basically, to vertically stretch it, I took these numbers and I multiplied everything by 2. Now the next thing is to take my new result and shift all those dots right by 1 and down 3. And when I do that, I just shifted all the new dots on my new graph here to the right by 1 and down by 3. And even though the graph looks smaller here, we kind of zoomed out because you can see my y values are now 6 here, whereas in my original graph, my highest y value was 4. So this is something that was translated right and down and stretched vertically double.